In this final video, I want to talk about cluster thresholding. And in particular, I'm also going to talk about small volume corrections too. So in cases where we have some sort of a priori hypothesis about where we would expect the activations to show up, then we can perhaps constrain this multiple comparison problem by applying that sort of anatomical spatial information to reducing the number of comparisons that we need to look at. So cluster thresholding also relies on Gaussian random field theory. And it's a slightly different way of applying it, but it's an interesting one. And the first step here is that you choose an arbitrary height threshold. So last lecture, I said the advantage to a voxel-wise thresholding approach is that you're not doing anything arbitrary. Those numbers are chosen for you from the data. Clusters thresholding work differently. You will start by choosing an arbitrary height threshold. And the key is, it really doesn't matter what you pick. There are implications, and we'll talk about what they are, but there is nothing that's right or wrong in terms of the way to do this. So for instance, and different software packages default to different height thresholds. So for instance, FSL, the Oxford package, defaults to a height threshold of Z of 2.3, or what would be an uncorrected p-value of 0.01. So here's a data set with 192 values in the X and 192 values in Y with particular smoothing. You can see it's quite a spiky little set. And if you threshold this data set at Z equals 2.3, then you can see that there are various peaks that have made it beyond that threshold. And I'm just sort of highlighting a lot of them there. In many ways, it's more valuable looking at this as an excursion set because it's easy to see which things have come through. And you get a variety of different peaks here. And they vary in their size. And that's the important thing here. So some of them are larger than others, but we have this empirical distribution of what we would expect to have happened by chance, just knowing that it was a Gaussian random field, if we chose this particular height threshold. And again, this is the Euler characteristic. This would be, at a Z of 2.3, we would have gotten to the point where we were still going up, and there's a massive number of peaks here that have happened by chance. So once we've specified this arbitrary height threshold, we then have to say, well, what are we going to accept by chance? And this is normally the default. We're going to accept a false positive rate of 0.05. So the probability threshold, P, will be 0.05. The height threshold, Z, was a Z of 2.3 in this case. And then we can say, well, look, based on this, I can see I have this empirical distribution of what I get by chance in a Gaussian random field. I could measure the number of clusters, but more than that, I can measure the size of those clusters, right? I could say, well, some of them are bigger than others, and I can actually measure them. And based on that, I get a probability distribution because I can characterize that both in terms of the mean size and in the variance. So in this particular case, when I calculate the mean cluster size, the number of voxels that are connected to one another, I get that there are, the mean is 22. Some are bigger, some are smaller, no problem. I can also calculate the standard deviation here, the variance, right? So in this case, there's a standard deviation of 17 voxels. That is to say, the noise is at size 17 voxels. And knowing the mean and the standard deviation, that gives me a null distribution, right? So what I can do is I can say, okay, I've got a mean, I've got a distribution, a standard deviation, a variance. Then I could say, well, when I compare that, if that's my null hypothesis, what would I need as an actual cluster size before I sort of said, well, I'm only going to have a 1 in 20 chance of that being a false positive. So that is to say, let me start this over. I have my mean, I have my variance, which means that I have a normal distribution. If I then went and said, well, where is the 0.05 cutoff on that distribution? Okay, how large would my cluster have to be before I would say anything above that has at most a 1 in 20 chance of being a false positive, which is very standard what we do with threshold and clusters. And in this case, it turns out that if you had 50 or more voxels together in a cluster, you would say that would have only a 1 in 20 chance of exceeding this random characteristic by chance. Hopefully that's made sense. The key here is we've chosen this arbitrary height threshold, Z of 2.3, and I chose that because that's what FSL uses. SPM uses 0.001. I'll go to that in a minute. But it's arbitrary. It was just a random decision. Then we said, well, what are we going to accept in terms of a family-wise error? Well, we're going to use 0.05 because that's what we always use by convention. Given that, we can compute this empirical distribution of what we would expect clusters to be in terms of their size just by chance, using the Euler characteristic. And then knowing that mean and standard deviation, we can say, well, where would we threshold that so that anything above it would only occur by chance less than our probability threshold of 0.05. That is a cluster threshold. So the key is we don't care so much about height in this. As soon as it passes whatever our arbitrary height threshold is, we throw all height information out and only care about how big the cluster is above that height. What we're saying is, what we're interested in is the size of the cluster. Little clusters are likely to occur by chance, and therefore we're not going to treat them as seriously. But large clusters are going to be less likely by chance, and therefore much more likely to be true physiological signals that are of interest to us. So this is a way of dealing with that problem that I suggested that voxel-wise cluster thresholds offer. That you may find that you have these large activations that are anatomically meaningful that are just a little bit below your very high height threshold. Well, if you lower the height threshold arbitrarily, in this case I've lowered it a lot because 2.3 is enormously less than something like 4.7, 4.9, then lots of things are going to be there. Sure, we get that. The way we separate what's signal from noise is by the size of the activation in this case, and that's what a cluster threshold is. As always, smoothing makes a difference. So smoothing, the more you smooth your data, the larger the clusters that you would expect to see by chance. So for instance, if you take exactly that same data set that I did before and double the smoothing, now the mean cluster size is 64 voxels and the standard deviation is even larger than that. So you can see there are fewer clusters and a couple of them are enormous, a couple of them are fairly small, but when you calculate the mean and standard deviation, you get a new distribution. And if you threshold that, you would say, well, the likelihood that something exceeds that by chance now requires that you have to have 210 connected voxels or more. So if you increase the smoothing, then you're going to make your cluster thresholding less sensitive because now, by definition, even the random clusters are larger. So you need still larger clusters to exceed that by chance. So it has different effects, right? So what I said before was if you increase the smoothing for a voxel-wise threshold, you decrease your statistical threshold. You increase your sensitivity to these larger clusters. If you're using cluster thresholds, increasing the smoothing decreases your sensitivity because they're measuring different things. One is based on height. Cluster thresholds are based on height. Cluster thresholds, so voxel thresholds are based on height. Cluster thresholds are based on spatial extent. And smoothing affects those two things in different ways. One of the things that people often do is they think, well, because there's some arbitrary decisions to be made here, I can play with some of these characteristics. And that's true. You can change the height threshold. And as I said, we're going to do that in a second. But often what people try to do is change the p-value instead. And there are multiple reasons why that's not an optimal thing to do. One is there's an accepted standard p-value that we all use, which is 0.05. So anytime you change it, you're going to raise people's eyebrows and they're going to wonder, why did you change it? What are you doing? If you were to make it like tighter, so if you go from 0.05 to 0.01, then you're going to increase the size of the cluster that you need to detect in order for it to be there, not by chance. So for instance, 0.05, given the previous example, gave us a voxel threshold of 210 voxels in a cluster to be significant. But if you make it more stringent, p-value of 0.01, then you're going to say, well, now it needs to be 280 voxels. So in other words, you're looking for even larger activation clusters. So it's not normally the thing that you want to do. Leave the p-value at 0.05 and you're in good shape. What you want to think about is changing the height threshold. So this is the original the original example I showed you, where there was a mean of 22 voxels and a standard deviation of 17 at a height threshold of 2.3. It was arbitrary. I picked it because that's what FSL uses. But what if you set it to a height threshold of 3.1? Equally arbitrary, and I picked it because that's what SPM uses. But I just wanted to sort of illustrate this. Now, obviously, with a higher height threshold, fewer of those little peaks in the Gaussian random field pass the threshold. And you can see that. There are fewer peaks, and they tend to be smaller little clusters once you do it, because, of course, you're higher up the mountain, as it were. Now, there's a mean of 4 voxels with a standard deviation of 3 in terms of our empirical distribution. And now when we look at what you need to be significant, like how many voxels do you need to be a significant activation, it's much smaller, right? So now you only need 9 voxels in a connected thing to exceed a height threshold of 3.1. And hopefully that makes perfect sense. That is to say, by raising the height threshold, now there are fewer things that are there by chance in terms of what's passing this threshold, and there's smaller little extents, which means that by raising that height threshold, you've increased sensitivity to smaller activations. Cluster thresholds have this weird counterintuitive behavior in that sense. So for a lot of people, the idea of increasing the height threshold causing an increase in sensitivity is counterintuitive. They sort of think, wait a second, I'm making it harder to pass this hurdle and yet I'm getting better sensitivity. How does that work? Well, I've just explained how it works. It works because by increasing that height threshold, you're decreasing what you would expect to be there by chance. And therefore, the threshold that you accept is greater than chance also decreases. As a result, cluster thresholds are one of the things that I think people find confusing. And I understand that. The advantages to a cluster threshold is this idea that it might be more sensitive to activations that are spatially large that are perhaps not quite as high, right? So in that circumstance where you have large anatomically meaningful activations that don't quite reach these great peaks that you need for voxel-wise thresholding, cluster thresholding is probably a perfectly sensible thing to do. There are a number of disadvantages here, though, right? One is that height threshold that you choose is completely arbitrary. No one can say right or wrong, which gives you a lot of flexibility when it comes to twiddling your data. You can try it at 2.3 and see whether you get what you want, and then you could try it at 3.1 and see whether that gives you what you want. And then if that doesn't, then what if you make it 3.4 or 2.7? So as long as you report what you did, you're honest about it, but there's a lot of scope for fiddling your results, and that's not a good thing. The other thing that's important that I think really almost always gets lost by people is it's not capable of giving you very precise activation, because all you can say is that this cluster exceeds this threshold by chance. You can't say that any given coordinate does, right? It's just not part of the valid inference that you can make. So for instance, if you have a big old cluster that maybe meanders a little bit so that it's in several different areas, like say it's in dorsolateral and ventrolateral prefrontal cortex and maybe goes even into premotor cortex, all you can say is that there's a cluster there. You cannot say with any confidence whatsoever, your statistics do not allow you to say you have activation in prefrontal, ventrolateral, dorsolateral, and premotor cortex. You have a cluster that includes some of those areas, and somewhere in there there's probably significant activation, but you can't say where it is. Very, very different than a voxel threshold, where you can say the peak of this cluster is here, and these are the coordinates in space to the millimeter, and this part of the brain is this region, right? Which is mostly what we want to be able to say. So you have to be very careful about the inferences that you can actually draw from cluster statistics. One of the things I pointed out was the effect of that height threshold, that arbitrary height threshold, can be counterintuitive for a lot of people. So for instance, if you want to increase your sensitivity, you need to increase your height threshold rather than decrease it. And the tendency is for most people to decrease it and discover they ain't gotten nothing. Or they end up with such a huge cluster that anatomically it's not meaningful. The other thing is, there was a paper a couple years ago by Tom Nichols' group saying that some of the results from cluster statistics are really, really questionable. So something, I think it was like 40% of the papers that use cluster statistics were shown to have artificially inflated false positive rates. So for all of these reasons, I just don't use them. I don't think that they're very useful, and I don't encourage you to use them as well. I would, as always, I encourage you to play with them, understand them, try them out for sure. But when it comes to reporting your data, I don't recommend using cluster thresholds. They're not wrong, but they are perhaps counterintuitive. The other thing that it's worth pointing out here is that I'm acting as if they're independent of one another, but they're not, right? Because if you change that initial height threshold up and up and up, you're going to get greater and greater sensitivity, because the effect of the expected cluster size is going to shrink and shrink and shrink and shrink. When it gets to the point that it's only going to be a value of 0.05, then it is exactly the height threshold. And that means that any single voxel that passes that is significant. So voxel and cluster thresholds exist on a continuum. If you're going to use cluster statistics, you're taking some extra risks because you're adding some arbitrary decisions in there, and those arbitrary decisions can have important consequences on what you consider active and what you don't, which in my opinion is not an ideal scenario. The other thing I want to talk about very briefly is, what if you have some a priori, that is to say, before you've collected your data, you have this idea of where you're expecting your activations. So you have an a priori region of interest. And then in that case, really, the fact that you collected the whole brain data is just a function of, well, that's what you get when you shove a head in the scanner. But actually, all I really care about is, the inferior parietal lobe in this. It's a numerical task, and I know from the previous literature that I'm expecting activation in and around the intraparietal sulcus. And this is, a relatively small constrained area of the brain. Why do I have to do multiple comparisons for like all of prefrontal and temporal lobe and occipital lobe when I know that I'm really interested in the intraparietal sulcus, right? That's the small volume that I'm interested in. And in that case, reducing the number of statistical comparisons is probably really very beneficial, because we're moving away from doing whole brain things where you've got a massive volume down to a really small volume. It's not like a quarter as small. It might be, a 20th as small, or even smaller than that, depending. So what's in there, what's in the small region of interest, still depends on the volume of that region of interest. But now you're talking about something that's really small. The smoothness and the surface area. So for instance, if you're interested in the intraparietal sulcus, which is, a sort of bumpy little line that separates your inferior from superior parietal lobes, the surface area is quite high, because it's more like a line than a sphere. If you were interested in like Broca's area or something like that, well, you might be able to draw sort of a little sphere around it, and that would be a reasonable approximation for it. So it's still important to bear in mind all of these factors affect the number of results within your small volume. The other thing to bear in mind is that not all inferences are equally valid in a small volume correction. So you can still apply Gaussian random field theory, but Gaussian random field theory that's used for voxel-wise corrections are fine within a small volume correction. Cluster thresholding depends really critically on having a good empirical distribution of the noise, so you can compare the size of the activations against the noise. What that means is that you need to have sort of about a minimum of, a heuristic here is a minimum of about 25 results within that small volume. If you have something less than that, then it's not going to get an accurate distribution of what the null distribution is, not going to get an accurate estimate of the null distribution, excuse me. And without that, you're going to have essentially crazy results, because you don't have sufficient data to compare your activations to. So for instance, if you expected like all of the intraparietal sulcus to be active, and maybe it's only like 12 results or something like that, and in fact it basically is, well, what do you compare that to? You don't have any null distribution there. You need noise. So cluster statistics work on the fact that you're trying to find clusters of activation in a larger area where there is also just noise. But the more focal you make your region of interest, which is probably what you think is a sensible approach, is the less likely that cluster statistics are to give you meaningful results. So what I would certainly say is, I've already said I'm not a huge fan of cluster statistics. If you're doing a small volume correction, don't use cluster statistics, right? It is probably almost certainly the wrong thing to do and will give you false results. If you're doing a small volume correction, then you really need to rely on voxel-wise height thresholds based on Gaussian random field theory. Again, a lot of material this week, but hopefully, despite the fact that it's intrinsically very mathematical and the papers that I'll recommend in the reading list can be heavy going, I've tried to make it as visually intuitive as possible using graphics rather than go through the math, because for a lot of people that's not intuitive. It's not easy to work through. If you are a math person, the papers are going to give you chapter and verse a detail of everything that you want. But today's take-home messages really concern, or this week's, take-home messages really concern the fact that t-test, which is the key statistical inference tool that we're going to be using, is really based on this threshold of effect size to noise. It's just a simple ratio. And that would be if we only had a single t-test. We could just use a standard 0.05 threshold. But we never are in that situation with fMRI. We always are dealing with multiple comparisons. It could be multiple comparisons across the whole brain, in which case you may have on the order of 25, 30,000 of them. You could have more if you're doing it with structural imaging. Or it could be that you have a small volume correction, in which case you've reduced that number rather considerably, but you still have a three-dimensional Gaussian random field in there, and that can be used to compute a corrected voxel-wise height threshold. And that automatically gives you a corresponding value that corresponds to 0.05 family-wise error across that volume. If you're using whole brain analysis, for instance, or at least large parts of the brain, like a hemisphere or something, then sure, you can also use cluster statistics instead of voxel-wise statistics, because in that case, you have a sufficiently large amount of data that's both possibly showing activations and not showing activations, that you get a good empirical distribution of what you would expect to pass that arbitrary threshold by chance. And based on that, you can then say, well, if beyond this size, I will accept that as a meaningful cluster, which is very different than, for instance, height thresholds, where we're going to accept even a single voxel that passes it by chance. In terms of the reading, this week I'd really like you to read Chapter 7 of the Poldrack book. Provides a reiteration of the things that we've talked about today, but in their terms, and it's always good to get this more than one way, because bits and pieces start to click. The more often that you process the information, the more different ways you hear it. The papers here are mathy, and I don't want that to be something that stops you, because if you're going to stay in FMR, there's just no way that you can avoid the mathematics. It doesn't mean that you need to be able to understand every little bit of it, and it doesn't mean that you need to be able to create the math yourself, but you can't sort of shy away from it either. At some level, you just need to work through it and try to understand what you can. And where you have questions, you can come to colleagues, you can come to me. I'm not the world's greatest mathematician either. I can handle it up to a certain level, and then I have to defer to colleagues who are more mathematically talented than I am. But for instance, the papers here are all key examples of how you can understand the statistical inference process. And even if you just work your way through one of them, and it doesn't matter to me which one you pick, you're on a winner there. So good luck with that.